Welcome back to the deep dive. Today we are cracking open the engine room of modern predictive analytics. We're talking about tree-based machine learning. And if you work in a regulated space, finance, accounting, you've definitely run into these. Random forests, gradient boosting,
Oh,
XGBoost.
yeah, they're the absolute workhorses. You see them everywhere, from forecasting to really critical risk classification.
Exactly. And that's our mission for this deep dive. We're focusing on you, the professional, who needs to understand not just how powerful these models are, but maybe more importantly, how reliable they are.
Right.
We're going to get into the history, the methodology, and the big question. Why have these specific models earned the trust of regulators and, those tough internal audit committees?
And that trust factor, that's really the core insight here.
Mm.
Because for high-stakes modeling, think credit risk, audit compliance, you can't just chase the highest accuracy score.
No, you'd get shut down fast.
You would. You need a model that gives you that high performance and a defensible reason for every single decision it makes. And that's why these tree-based methods are, frankly, indispensable today.
Okay, so let's unpack that history then, because like you said, these aren't some brand new invention. They have a long academic history.
Hey, dude.
We should probably start back in the early 80s with what's really the foundation of it all, the publication of CART.
Right, CART classification and regression trees. That was 1984.
And this was a huge deal. This work by Brayman, Friedman, Olshan, and Stone, it introduced what they called binary recursive partitioning.
Which sounds incredibly technical.
It does, but the idea is pretty simple, right? It's just about repeatedly asking the most efficient yes or no question to split up your data.
Exactly. If you were trying to predict a category, you'd use a classification tree. And you'd use math like Giannini impurity to find the best split, which is just a fancy way of measuring how mixed up your data is.
And for predicting a number like revenue.
Then you'd use a regression tree, and you'd be trying to minimize the mean squared error, the MSE.
So a single decision tree was great because it was so easy to interpret. You could literally draw it out like a flowchart.
You could, but it had a fatal flaw. It was incredibly prone to overfitting.
What does that mean in this context?
Think of a single tree as a student who memorizes every single question and answer on a practice test.
Okay.
They'll get a perfect score on that specific test, but give them a slightly different exam, and they just fail completely.
Because they never learned the actual principles, they just memorized.
Exactly. They can't generalize. And to solve that, the research world moved toward ensemble thinking, this idea of combining many weak models into one really powerful, stable one.
And that move brings us into the late 90s and really the early 2000s with the development of random forests.
By Leo Breiman again in 2001. This was built on his earlier work with something called bagging.
Bagging, or bootstrap aggregation, it sounds a bit technical, but the core idea is running things in parallel.
That's a great way to put it. You're training hundreds of these decision trees all at the same time.
But you're not giving each tree the same data. You give each one a slightly different random sample of the training data.
And, crucially, a random subset of the features, too.
So here's the question that I think confuses people. If you're training hundreds of mediocre or even overfit trees on their own, why doesn't that just average out to, noise?
Yeah, that's the key distinction, and it's a brilliant one. The power is in that randomness. It forces the trees to be different from one another.
It decorrelates them.
It decorrelates them, exactly. Because each tree only sees a random sliver of the data and the features. Their individual mistakes are mostly independent. So when you average out the predictions from all of them, the random errors and that instability, the variance, it just cancels out.
So it's like the wisdom of the crowd.
It's the democratic approach.
Yeah.
Everyone gets a vote, and the collective decision is way more stable and reliable.
Okay, so if random forests are the parallel democratic effort, the next big evolution was the complete opposite. It was sequential and hyper-focused.
Right. Now you're talking about gradient boosting.
This is where we get into the really state-of-the-art models we see today. In the 2000s, another one of the same researchers, Jerome Friedman, introduced gradient boosting machines, or GBMs.
And this completely flipped the script. We stopped training trees independently.
And started training them sequentially, one after the other.
Yeah. I like to use an analogy here. Imagine you're editing a really complex report. Random forest is like sending that report to 20 editors at once and then averaging their feedback.
Okay.
Gradient boosting is like hiring editor 1 who finds the 100 biggest mistakes.
Yeah.
Then you hire editor 2 whose only job is to fix the mistakes that editor 1 left behind.
And then editor 3 fixes the mistakes of editor 2.
Precisely. Each new small tree is built specifically to correct the mistakes, the residuals of the entire group of trees that came before it.
That refinement process sounds incredibly powerful.
It is. It leads to extremely accurate predictions, which is why the modern versions, XGBoost, LightGBM, CatBoost, they just dominate enterprise use cases today. They're just highly, highly optimized versions of this sequential process.
So just to make sure we've got the foundations clear before we jump into the compliance side of things, all of this, whether it's boosting or bagging, is built on that simple decision tree.
Absolutely. The decision tree is that simple, interpretable foundation. It's just a flowchart of rules.
Yeah.
Pick the best feature, age, credit score, whatever, to split the data.
And you just keep splitting?
You keep splitting until you isolate groups that are very pure, like, say, a node where 98% of the people in it have defaulted on a loan.
Yeah.
It's very easy to visualize and follow that logic.
But the complexity and the huge jump in accuracy, that comes from the ensembles.
It does. Random forests get their stability from running in parallel and averaging. Gradient boosting gets its extreme precision from that sequential error correction. And knowing that difference is really key to knowing which one to use and when.
Which brings us to the most critical part for our listener, the person working in that regulated space. We've got the accuracy, but now we have the regulatory litmus tests of the 2020s. Regulators don't just ask what you predicted anymore. They demand to know why. If a model is flagging fraud or granting credit, you absolutely need an auditable decision trail.
There's no way around it.
And this is really where tree methods separate themselves from, say, deep learning models. They have these amazing explainability tools built right on top of them.
You were talking about things like SHAP values.
Exactly. SHAP values Shapley additive explanations, and also things like feature importance or visual tools like partial dependence plots.
And the reason SHAP values work so well with trees is that they can assign a fair, mathematically rigorous amount of credit to every single input feature for its contribution to the final output.
A perfect attribution.
A perfect attribution.
Yeah.
Because a tree makes decisions based on specific splits and paths, the SHAP algorithm can trace those contributions right back to the inputs. So you get this crystal clear explanation.
Which is exactly what an auditor wants to see.
It's what everyone wants to see. It satisfies internal audit, it satisfies model risk management, and it satisfies the external regulators all at the same time.
So let's just address the big question head on then. Why are regulators so comfortable with this specific class of models?
I think it comes down to three main things. First, it's the long history.
Right.
Tree-based methods have been used in finance for decades. We're talking about established models for PD, LGD, EAD probability of default, loss given default.
All the core credit risk metrics. They're also used for things like IFRS 9 staging, which is fundamental to modern financial reporting.
Exactly. So that long track record provides a huge amount of regulatory comfort. They aren't some new, untested thing.
What's the second reason?
The high level of explainability we just talked about. You move beyond just saying these things are correlated, and you provide an actual auditable decision trail. The tree structure plus SHAP values makes the logic transparent.
And the third?
Finally, just their widespread adoption. They've been validated across millions of use cases, which makes them inherently lower risk than some of the newer, more black box models. They're robust, they're stable, and they scale well.
Okay, let's make this really concrete. Can you give us a couple of real-world finance examples?
Sure.
Let's start with credit risk classification using, say, a random forest.
Okay. A traditional model might just spit out a number, like a 70% probability of default.
Right.
A random forest does that too, but because of its structure, you can immediately pull up the feature importance, the SHAP values. The model can tell the analyst that it wasn't just the low credit score. It was the low score plus the fact the customer had 3 recent missed payments and high credit utilization that pushed them into that high-risk bracket.
It tells you the why.
It tells you the why.
Okay.
Now let's switch to forecasting. Let's say you're forecasting financial metrics with something like XGBoost.
Predicting loan originations maybe or operating expenses.
Exactly. These models are incredible at that because they capture complex, nonlinear relationships that a simple linear model would just completely miss.
What do you mean by nonlinear?
Well, for example, a linear model would have trouble if your sales only spike when a marketing incentive crosses a specific threshold, like exactly $1,000.
Oh, okay.
For a tree model, that's easy. That's just another decision split. Is the incentive greater than $1,000? So for anyone in finance, from an analyst to the CFO, the value is just undeniable. You get peak accuracy and the transparency you need for compliance.
Which I think brings us to the end of our deep dive. We've really covered the whole journey, haven't we? From CART's simple foundation all the way to the power of XGBoost, and how it's all secured by explainability tools like SAP.
Yeah, the ultimate synthesis here is that tree-based methods are just uniquely suited for modern finance. It's a perfect marriage of high performance and regulatory comfort.
Decades of academic history meeting the demands of today.
Exactly. Proven history, guaranteed performance, and most critically, auditability.
So let's leave our listener with one final provocative thought.
Okay, so if we agree that transparency is the ultimate currency for trust in these regulated environments, and we know that tree-based models, through tools like SHAP, force us to look at the why behind a prediction. Consider this. What fundamental, maybe nonlinear assumptions about your business drivers or your customer behavior might you be missing right now, simply because your current models aren't transparent enough to force you to look at that underlying logic? That power to understand the why, that's the real competitive edge here.